FlowFile repository in Apache NiFi. Now we are focusing on FlowFile repository. The FlowFile repository is where NiFi keeps tracks of the state of what it knows about a given flow file that is presently active in the flow. The implementation of the repository is pluggable. The default approach is a persistent write-ahead log located on a specified disk partition. Here you can see pass-by reference. An important aspect of flow-based programming is the idea of resource constraint relationships between the black boxes. In NiFi, these are queues and processors respectively. Flow files are routed from one processor to another through queues simply by passing a reference to the flow file, similar to the claim check pattern in EIP. In the web crawler flow here, in Invoke HTTP processor reaches out to the URL with an HTTP GET request and adds the status code attribute to the flow file depending on what the response was from the HTTP server. After updating the flow file's file name in the update attribute processor after invoke HTTP, there is a root on attribute processor that routes flow files with the successful status code attributes to different processors. Those that are unmatched are dropped by the root on attribute processor because it is configured to auto terminate any data that does not match any of the routing rules. Coming into the root on attribute processor, there is a flow file F1 that contains the status code attribute and points to the content C1. There is a provenance event that points to C1 and include a snapshot of F1 but is omitted to better focus on the routing. This information is located in the flow file content and provenance repos respectively. After the routing root on attribute processor examined the flow file status code attribute, it determines that should be routed to two different locations. First thing that happens is the processor clones the flow file to create F2. This copies all of the attributes and the pointer to the content. Since it is merely routing and analyzing the attributes, the content does not change. The flow files are then added to the respective connection queue to wait for the next processor to retrieve them for the 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 provenance reported documents, the change that occurred, which include clone, include the clone and 2 root events. Each of these events has a pointer to the relevant content and contains a copy of the respective flow files in the form of snapshot. Here you can see update update attributes, process is connected with success, and success is connected to pass root on attribute. Root on attribute is interact with Q0, here Q, and this Q is connected to remove duplicate in detect duplicate process, and root on attributes interact with Q here, and Q is connected to log attribute here, and in before F1 is connected to F. Basically, F1 is pointing to C1 in FlowFile, and here in the content you can see C1, and in after update attributes interact with Q, and Q is connected to root on attribute here, and root on attribute interacts with Q, and Q is connected to detect duplicate here, and pass root on attributes interact with Q here, and Q is connected to log attributes, and here in the FlowFile repository F1 is pointing to C1, and F2 is pointing to the C1 here, and in the content repository you can see C1 here, and in provenance in clone P1 is pointing to F2, and in root P2 is pointing to F1, and in root P3 is pointing to F2. Here you can see the FlowFile repository contains metadata about the files currently in the flow. NiFi claims to be reliable. How is it in practice? The attributes of all the flow files currently in use, as well as the reference to their content, are stored in FlowFile repository. At every step of the pipeline, modification to a flow file is first recorded in the FlowFile repository in a write ahead log before it. For each flow file that currently exists in the system, the FlowFile repository stores the FlowFile attributes, pointer to the content of the flow file located in the FlowFile repository, state of the state of the flow file, for example, to which queue does the flow file belongs at this instant. The FlowFile repository gives us the most current state of the flow, thus its a powerful tool to recover from an outage. NiFi provides another tool to track the complete history of all the flow files in the flow. The provenance. As an example, we can consider the interface FlowFile repository. Implementations must be as an example, we can consider as an exception example, we can consider this exception occurred in initialize method in interface flow file repository here. IO exception, and it's if it is unable to initialize the repository. As an example too, we can consider commit. When the commit method is called, the flow file's new state is persistent in the flow file repository, and any provenance events that occurred are persisted in the provenance repository. The previous content is destroyed unless another flow file references the same piece of content, and the flow files are referred to the outbound queues so that the next processors can operate on the data. Here commits the current session, ensuring all operations against flow files within this sessions are atomically persisted. All flow files operated on within this session must be accounted for by transfer or removal of, or the commit will fail. This method is available in the interface process. As an error example, as an exception example, too, we can consider this one, flow file handling exception. If not all flow files acted upon within this session are accounted for by user code such that they have a transfer identified or were marked for removal, automated rollback occurs. This exception can occur in commit method in interface process. As an example 2, we can example 3, we can consider property NiFi.flowfile.repository.implementation. The flow file repository implementation, the default value is org.apache.nifi.controller.repository.write ahead flow file repository. The other current options are org.apache.nifi.controller.repository.volatile flow file repository and org.apache.nifi.controller.repository.rocksdb flow file repository. This property is available in NiFi.properties file. Now we are considering write ahead flow file repository in system properties. Write ahead flow file repository is the default implementation. The class write ahead flow file repository, we expose the property named NiFi.FlowFile.repository.always.sync, that is a boolean value indicating whether or not to force WALI to sync on each update. By default the value is false. This is needed only in the situation which the power loss is expected and not mitigated by uninterruptible power sources, UPS, or when running in an unstable virtual machine, for instance. Otherwise we will flush the data that is returned to the operating system, and the operating system will be responsible to flush its buffers when appropriate. The operating system can be configured to hold only a certain buffer size or not to buffer at all as well. When using UPS, this is generally not an issue as the machine is typically notified before dying, in which case the operating system will flush the data to disk. Additionally, most disks on enterprise servers also have battery backups that can power the disks long enough to flush their buffers. For this reason, we choose to, instead of not to sync to disk for every write, but instead sync only when we checkpoint. This is in the package org.apache.nifi.controller.repository. The write-ahead flow file repository is the default implementation. It persists flow files to disk and can optionally be configured to synchronize all changes to disk. This is very expensive and can significantly reduce NiFi performance. However, if it is false, there could be a potential for data loss if either there is a sudden power loss or operating system crashes. The default value is false. Here you can see the property NiFi.flowfile.repository.wal.implementation. If the repository implementation is configured to use the write-ahead flow file repository, this property can be used to specify which implementation of the write-ahead log should be used. The default value is org.apache.nifi.wali.sequential access write-ahead log. This version of the write-ahead log was added in the version 1.6.0 of the Apache NiFi and was developed in order to address an issue that exists in the older implementation. In the event of power loss to operating system crash, the old implementation was susceptible to recovering flow files incorrectly. This could potentially lead to wrong attributes or content being assigned to the flow file upon restart. Following the power loss to OS crash, however, one can still choose to opt into using previous implementation and accept that risk if desired. For example, if the implementation were to exhibit some unexpected error, to do so, set the value of this property to org.wali.minimal locking write-ahead log. Another available implementation is org.apache.nifi.wali.encrypted sequential access write-ahead log. If the value of this property is changed upon restart, NiFi will still recover the records written using previously configured repository and delete the files written by previously configured implementation. Now we are considering encrypted read-write flow file repository properties. The property NiFi.flowfile.repository.encryption.key.provider.implementation. This is the fully qualified class name of the key provider. A key provider is a data store interface for accessing encryption key to protect content claims. There are currently 3 implementations. Static key provider, which read a key directly from NiFi.properties. File-based key provider, which read the keys from an encrypted file, and key store key provider, which read keys from the standard security java.security.keystore. Now we are considering volatile FlowFile repository. To use this implementation, set NiFi.flowfile.repository.implementation to org.apache.nifi.controller.repository.volatile FlowFile repository. The class volatile volatile FlowFile repository, an in-memory implementation of the FlowFile repository. Upon restart, all flow files will be discarded, including those that have been swapped out by the FlowFile swap manager. This is in the package org.apache.nifi.controller.repository. The volatile FlowFile repository, this implementation stores FlowFile in memory instead of on disk. It will result the data loss in the event of power machine failure or restart of NiFi. To use this implementation, set nifi.flowfile.repository.implementation to org.apache.nifi.controller.repository.volatile flow repository. Now we are considering RocksDB flow file repository. RocksDB, to use this implementation, set the NiFi.flowfile.repository.implementation to org.apache.nifi.control.repository.rocksdb flow file repository. This is in the package org.apache.nifi.control.repository. The RocksDB flow file repository is deprecated in the favor of write-ahead flow file repository. It will be removed in future major versions of Apache NiFi. To use it in NiFi 1.x, you must download NiFi RocksDB now from the Apache Nexus repository and place it in your NiFi lib directory. This implementation makes use of RocksDB key value store. To use it uses periodic synchronization to ensure that no created or received data is data is lost as long as nifi.flowfile.repository.rocksdb.accept.data.lost is set false. In the event of failure, for example power loss, work done on flow files through the system, that is routing and transformation, may still be lost. Specifically, the record of these actions may be lost, reverting the affected flow files to a previous valid state. From there, they will resume their path through the flow file as normal. This guarantee comes at the expense of the delay of an operation that add new data to the system. This delay is configurable as nifi.flowfile.repository.rocksdb.sync.period and can be turned to the individual system. The configuration parameters for this repository fall into two categories: NiFi-centric and RocksDB-centric. The NiFi-centric settings have to do with the operations of the NiFi, operation of the flow file repository and its integration with NiFi. The RocksDB-centric settings directly correlate to the settings on the underlying RocksDB repo. Here you can see RocksDB centric configuration properties: nifi.flowfile.repository.rocksdb.parallel.threads. The number of threads to use for flush and compaction. A good value is the number of cores. The default value is 8. Now we are considering swap management. The property NiFi.swap.manager.implementation. The swap manage implementation, the default value is org.apache.nifi.control.file system swap manager. There is an alternative implementation, encrypted file system swap manager, that encrypts the swap file content on disk. This encryption key configured for the FlowFile repository is used to perform encryption using AES GCM algorithm. In swap management, the NiFi keeps the FlowFile information in memory, the JVM, but during surges of incoming data, the FlowFile information can start to take up so much of the JVM that supports performance suffers. To counteract this effect, NiFi swaps the FlowFile information to disk temporarily until more JVM space becomes available again. These properties govern how that process occurs. Now we are considering FlowFile repository. In repositories, the system computes a new base checkpoint by serializing each FlowFile in the hash map and writing it to a disk with the file name .partial. FlowFile, the FlowFiles that are actively being processed by the system are held in the hash map in the JVM memory. This makes it very efficient to process them, but requires a secondary mechanism to provide durability of data across processes. Process restart due to number of reasons, such as power loss, kernel panics, system upgrades, and maintenance cycles. The FlowFile repository is a write-ahead log or a data record of the metadata of each FlowFiles that currently exist in the system. This FlowFile metadata includes all attributes associated with the FlowFile, a pointer to the actual content of the FlowFile which exists in the content repo, and the state of the FlowFile, such as which connection queue or queue the FlowFile belongs in. The write-ahead log provides NiFi the resiliency it needs to handle restart and unexpected system failures. The FlowFile repository acts as NiFi write-ahead log, so as the FlowFiles are flowing through the system, each change is logged in the FlowFile repository before it happens as a transactional unit of work. This allows the system to know exactly what step in the node is on when processing a piece of data. If the node goes down while processing the data, it can easily resume from where it left upon the restart. The format of the FlowFiles in the log is a series of deltas or changes that happens along the way. NiFi recovers a FlowFile by restoring a snapshot of the FlowFile created when repository is checked, pointed, and then replaying on each deltas. The snapshot is automatically taken periodically by the system, which create a new snapshot for a FlowFile. The system computes a new base checkpoint by serializing each FlowFile in the hash map and writing it to the disk with the file name .partial. As the checkpoint proceeds, the new FlowFile baselines are returned to the .partial files. Once the checkpoint is done, the old snapshot file is deleted and the .partial file is renamed snapshot. The period between the checkpoints is configurable in the NiFi.properties file. The default is a 2-minute interval. Now we are considering the effect of the system failures on transaction in FlowFile repository. The node either accept the snapshot or delete the .partial if exists, or renames the .partial file to snapshot if the snapshot file doesn't exist. NiFi protects against the hardware and system failures by keeping a record of what was happening on each node at the time in their respective FlowFile repo. As mentioned before, the FlowFile repo is a NiFi write-ahead log. When the nodes come back online, it works to restore its state by first checking for the snapshot and the .partial files. The node either accept the snapshot and delete the .partial files if exist, or rename the .partial file to snapshot if the snapshot file doesn't exist. If the node was in the middle of writing content when it went down, nothing is corrupted thanks to the copy on write and immutably paradigms. Since FlowFile transaction never modify the original content pointed to by the content provider, the original is safe. When NiFi goes down, the write claim for the change is opened and then cleaned up by the background garbage collection. This provides rollback to the last known stable state. The node then restore its state from the flow file. The setup in terms transactional unit of work allow NiFi to be very resilient in the face of adversary, ensuring that even if NiFi is suddenly killed, it can pick up without any loss of data. Now we are considering flow files in memory and on disk in deeper view. This occurs when the number of flow files in the connection queue exceed the value set on the NiFi.queue.swap.threshold. The term flow file is a bit of a misnomer. This would lead one to believe that each flow file corresponds to a file on disk, but that is not true. There are two main locations that flow file attributes exist: the write ahead log that is explained before, and the hash map in working memory. This hash map has a reference to all of the flow files actively being used in the flow. The object referenced by this map is the same one that is used by the processors and held in the connection queues. Since the flow file object is held in the memory, all which has to be done for processor to get the flow file is to ask process session to grab it from the queue. When a change occurred in the flow file, the delta is written out to the write ahead log and the object in memory is modified accordingly. This allows the system to quickly work with the flow files while also keeping track of the what has happened and what will happen when the session is committed. This provides a very robust and durable system. There is also a notion of swapping flow files. This occurs when the number of flow files in a connection queue exceed the value set in the NiFi.queue.swap.threshold property. The flow files with the lowest priority in the connection queue is serialized and written to the disk in the swap file in batches of 10,000. These flow files are then removed from the hash map mentioned above, and connection queue is in charge of determining when to swap files back into memory. When the flow files is swapped out, the flow file repo is notified and it keeps a list of the swap files. When the system is checkpointed, then snapshot includes a section of the swap out files. When swap files are swapped back in, the flow files are added back into the hash map. This swapping technique, much like a swapping performed by most operating systems, allow NiFi to provide a very fast access to the flow files that are actively being processed while still allowing many millions of flow files to exist in the flow without depleting the system memory. As an error example, we can consider this flow file repository. Now this is the end of my presentation. Thank you very much for watching it.